In this example, we're dealing with a bullet that has been shot straight up into the air. It is given an initial velocity of 335 meters per second. Now, by giving the velocity a positive value, I've just defined direction. Up is positive, down is negative. The bullet's in free fall, so its acceleration is negative 9.8 meters per second squared. The acceleration is negative because the acceleration is pointed downwards. Now, you might think that's all that we know, but there's actually one more piece of information given in the problem. We're asked to determine the maximum height of the bullet. The maximum height of the bullet will occur when its final velocity, v, is 0. After all, the bullet gets shot straight up into the air, so it's moving upwards. Gravity is accelerating it downwards, so the bullet will slow down. It will keep slowing and slowing until eventually its velocity reaches 0. At that point, it simply can't go any higher. As a matter of fact, it will begin to fall. Because the velocity is 0, the acceleration is negative, so the velocity will become negative. So the maximum height of this bullet occurs when its velocity is 0. So that's another piece of information we know. Since we're looking for the height, that's displacement, or delta x. Okay, now we've determined everything we know and everything that needs to be determined. What equation do we use? We need an equation that relates velocity, acceleration, and displacement. What about this one? V squared equals v naught squared plus 2a delta x. All right then, let's plug into the equation. V is 0, v naught is 335 meters per second, a is negative 9.8 meters per second squared, and delta x is what we need to figure out. All right, let's solve for delta x. We'll take 335 meters per second quantity squared and subtract it from both sides of the equation. That will make it disappear on the right and appear as a negative on the left. Next, we divide by 2 times negative 9.8 meters per second squared. When we do that, it will disappear on the right and reappear in the denominator of the left-hand side of the equation. All right, so delta x is negative the quantity 335 meters per second squared divided by 2 times negative 9.8 meters per second squared. When I square 335 meters per second, I get 112,225 meters squared per second squared. I'll do significant figures later. When I multiply 2 times negative 9.8, I get negative 19.6. Look at the units. The square on meters cancels, and the second squareds cancel completely, so in the end we're left with meters. That's good because we're figuring out displacement. When I work through the numbers, I get 5,700 or 5.7 times 10 to the 3. I'm limited to 2 significant figures because even though 335 has 3 significant figures, 9.8 has only 2. So we know that the maximum height of this bullet is 5.7 times 10 to the 3, or 5,700 meters. All right, now let's deal with the second part of the example. In this part of the example, we're throwing a rock up into the air, but we're on a bridge, so the rock can fall all the way down to the water if it has the time. All right, now what do we know? The first thing we know is the initial velocity of the rock. It's given an initial velocity of 2.3 meters per second up. So, since I'm reporting v naught as positive 2.3 meters per second, that means up is positive. Well, the rock's in free fall, so the acceleration is negative 9.8 meters per second squared. It's negative because the acceleration due to gravity points downward. If up is positive, then down has to be negative. We also know that time is 0.60 seconds. And the question is, at that time, what's the displacement of the rock? Okay, well that's everything we know. Now we need to figure out which equation to use. We need an equation with displacement, initial velocity, time, and acceleration. That's this equation. Delta x equals v naught t plus 1/2 at squared. All right, let's plug in the numbers. We don't know delta x, that's what we're looking for. But v naught is 2.3 meters per second, t is 0.60 seconds, acceleration is negative 9.8 meters per second squared, and t once again is 0.60 seconds. If I look at the units, in the first term of the equation, the seconds cancel, leaving only meters. That's good because we're looking for displacement. In the second term of the equation, seconds squared cancel, leaving once again only meters. That's good because we're looking for displacement. Now let's work out the numbers. Since I've got an equation here where I'm multiplying and then adding, I'll have to multiply the terms out first. The first term, when I multiply the numbers and round to 2 significant figures, I get 1.4 meters. In the second term, when I multiply the numbers and round to two significant figures, I get negative 1.8 meters. So delta x is 1.4 meters plus negative 1.8 meters, or negative 0.4 meters. So the solution to this problem isn't so bad, but the question is, what does the answer mean? Delta x, or displacement, is negative 0.4 meters. Well, remember, negative means down. That's the way we defined our directions. So if the displacement is negative 0.4 meters, that means the rock is displaced 0.4 meters down. In other words, the rock will end up 0.4 meters below the point where it was thrown. So now you get an idea of how powerful this equation is. This equation can track the position of the rock as it goes up in the air, as it falls back down, and even as it falls below where it initially started. All of that from one equation. That's pretty powerful stuff.